Howdy everybody, welcome back to Lab Hours. Today is the second of the two lectures, mini lectures on common distributions, common probability distributions. Let's talk about them. We're going to talk about the chi-squared distribution, we're going to talk about the t-distribution, and then we're going to talk about the central limit theorem. And we're going to talk about why all that stuff is super cool, how it relates to the normal random variables, everything you'll need to know, because this is actually right before the second midterm if you're still taking the class and the curriculum looks the same. So we're basically just going to cover everything you need to know for the midterm and almost nothing else, right? We're going to talk really a lot about these chi-squared and t-distributions after the midterm in these next sets of lectures once we start doing things like hypothesis tests and confidence intervals. So for now, we're just going to get you acquainted with the charts, how to use them, and how these things kind of relate to each other. So that's all we're going to do today. Hopefully we're going to be able to keep it as a shorter video, but it's kind of a theme on the channel where I say that and then it turns into a 35-minute lecture. So at least it's not an hour 15 like the classes are, right? Let's jump right in. Let's talk about the chi-squared distributions. Let's say, for example, I have a random variable w, and it is distributed as the following: a chi-squared. Chi is a Greek letter. It is the predecessor to our modern letter x. What is its parameter, right? W is distributed as a chi-squared random variable. That's what this means. W is distributed as a chi-squared random variable with parameters, what? In this case, it's this, which is a lowercase Greek letter nu. You might think it's the predecessor to v, but it's actually the predecessor to n, right? You can kind of see that, hopefully, in cursive. Ka-chow, right? Anyway, what does this mean? Well, this nu right here, for now, all you need to know is that it's a number. Later, we'll actually start talking about what degrees of freedom are. And in fact, the concept of what a degree of freedom is actually a little bit outside the scope of this class. It's something you'll talk about more in Intro to Econometrics if you move on to take that class, if you're taking classes if you're a student, or if you continue to study it if you're not, right? So all we need to talk about now is just like some properties of the chi-squared table and how its table looks different from the normal table that we talked about last time, okay? I'm not going to give you like the expected value, the variance, that's all on the table. The PDF is ugly, but once again, you need to know that this is another one of those like distributions like the normal distribution from last time that can take on a bunch of different values, right? So W could be distributed as like a chi-squared 6 random variable, or it could be distributed as a chi-squared 2000 random variable. That number is always going to be positive, by the way. It's counting something, but you don't know what it's counting yet, and that's okay. But again, we face the problem of this isn't actually quite integrable. However, we can approximate it, and the nice thing is that we have tables of approximations for common values. So let's actually just go pull that up really quick. Again, if you don't remember where we're getting this from, we're going to tmorg.org/downloads, right? Just really quick, if you forget about that, tmorg, right? And there we go, okay? tmorg.org/downloads. This is the first thing on the page. Let me just type it up again really quick. I don't know where that went. Boop. There we go. It's this document right here. You could be able to download it from there. It'll pull you up to this screen, okay? Chi-squared, right here, with parameter nu. Again, the mean is going to be nu, which is super nice, super convenient. The variance is 2 nu. But again, this is all on the table for you. This is gross, and you can see, again, we have an e raised to a negative exponent in our integral, which makes it super awful. Here is the z table that we've talked about. Down here, we have a chi-squared table, and this one is very different from the, well, so it's not very different, but it is different, okay? For one thing, I want to point out that this table that we talked about in the last lecture has this highlighted part on the table to the left of z, right? So over here, you see a z value, and then to the left of it is filled in. Underneath, it says the table entry for z is the area under the standard normal curve to the left of z, okay? And like we talked about last time, I'll pull this back really quick, I could just draw my normal variable, find stuff to the left of it, just like we did last time, right? That's what we did. And we found that using the exact z-score. Chi-squared is different, though. Chi-squared is the funkiest one. First of all, you'll notice there's this little, where it's giving you the line, right? Where it's giving you the line and says chi-squared alpha underneath it, that's kind of like up here where we had z and we had a line, a bar on the chart, if you will. But this one is interesting because it actually has a little alpha filled in the filled in part of the graph. So the really funky thing here, all right, alpha, when we're talking about the chi-squared table, is going to be the probability to the right of the value that you've picked. Okay? Just think about that, right? I'm picking the value that has alpha to the right of it. And you can remember this with the table. Like, you're going to have this chart. So if you can just remember, okay, normal table to the left. That's the filled in part. Chi-squared alpha, alpha's to the right. But then we're going to get to another crazy thing. Alpha is a probability here, right? It's the area under the curve to the right of this value. But you'll notice we only have certain columns. These numbers in here, they can't be probabilities because some of them are bigger than 1. In fact, most of them are bigger than 1. So how can these be probabilities? The answer is they're not, right? The probabilities are these alphas, right? So this chi-squared column that's chi-squared 0.9. What that is telling you is every single value in this column is going to be a chi-squared number on this number line, a bar that you can draw on the number, on the graph, that is going to have 0.9 or 90% of the area under the total curve to the right of it. Now, the really interesting thing about chi-squared, and I'll actually draw this out for you, is that it is not centered. It is not symmetric. It has a little hump and then kind of goes out like that, as you see from, this picture right here. It has a hump and then kind of extends outward. And the really interesting thing is that it gets like steeper the fewer degrees of freedom you have, right? Let's make sure that that makes sense intuitively. Degrees of freedom 1. That would be new 1. So that looks like, and in fact, let me just post this over here on the side again really quick so we don't have to keep scooting back and forth. Okay. Let's draw this graph and let's imagine that this is the chi-squared 1 degree of freedom, the graph, the PDF for that. And in fact, let's try and draw it straighter, just so that it's a little bit easier to see everything, right? That's silly. Okay? What does this mean? Well, this column over here, this chi-squared 0.9, says that the value on this graph, right here, this one that I'm drawing, chi-squared 1, because again, we're in the chi-squared degrees of freedom 1 row. So the value on this graph that has 90% of the distribution to the right of it, so maybe right here-ish, something like that, is 0.0157908, ... Pretty interesting. Let's take a look at the chi-squared, let's take a look at the chi-squared 100 degrees of freedom value. The same probability value on this graph, let's draw it like this, right? That same probability value, the one that has, 90% of the area of under the curve to its right, that value on this distribution, on the chi-squared 100 distribution, is actually 82.3581. 100 in the same column, 82.3581. So I drew them similarly, but actually this part right here has kind of shifted way out. In fact, it's something like this now. It starts to approximate a normal curve, fun fact, but we'll get into that later. The thing to notice is that this number and this number are both representing the same probability value because they're in the same column. But they're different numbers because they come from different graphs. They come from different distributions. Okay? That's basically all you have to know here. The other funky thing to point out, though, and I cannot stress this enough, these chi-squared values have alpha to the right. But the z-scores, the z-probabilities that are in the middle here from last time, they're to the left, right? So z, -3, first of all, z's can be negative, but like z0 is 1/2, right? From last time. The probability that you get a z-score for the standard normal table to the left of 0 is 1/2, right? But for this chi-squared, the probability that you get one less than 0 is impossible. It's 0 because it starts at 0. But even if it couldn't, right, you would need to find the alpha greater than and then do 1 minus that, right? So what if I wanted to find the value of W such that the probability of W being less than, you know, let's just say 82.3581, just coming up with that off the top of my head, right? Let's just think about that. If I know I have a, I don't know, chi-squared 100, just to pull one out of the hat, right? If W is distributed as a chi-squared 100 random variable, what is the probability that W is less than 82.3581? It's 10%. What does this mean about this 82 value? This 82.3581 on the chi-squared 100 distribution is the 10th percentile value. It means it is bigger than 10% of all other values that you will see across your entire sample, right? You're going to mostly see samples around here. You're going to see a couple that show up out here, and you'll see some of these, but if you've got a score that's only 82.3581, you're only going to expect to be a bigger score than 10% of the other people who are pulling chi-squared scores. And we'll talk more about like how we'll do that and what purpose that has later. For now, just know this is how you read the chart. And the nice thing about this one is you don't just have tiny values, right? You don't have just this side, but on the next page, you also have, you know, the 0.1 to the left, right? The 10% to the left, or the 5% to the right, my bad. 10% to the right, 5% to the right, or 90% to the left. So if I wanted to find the 90th percentile value, right, what I would do on this chi-squared 1 in this first row, degrees of freedom 1, chi-squared 0.1, this one has 10% of the area under the distribution to the right of it. That value would be 2.70554. That would be the 90th percentile value, because 90% of the values that you see based on their probabilities, if you repeat this infinite number of times, 90% of the values you see are going to be smaller than 2.70554 on this chi-squared 1 graph. That's everything we're going to need to do for chi-squared 1, okay? Well, for chi-squared in general. Other than a couple of interesting things, if you add together two chi-squared distributions, so like imagine W1 plus W2, and they're both chi-squared, that's going to be equal to, well, they're going to not be equal to, but it's going to be distributed as a chi-squared random variable with degrees of freedom 1 plus degrees of freedom 2, right? It's just going to get more variable as it goes on. There's just some fun stuff like that. You'll get most of that from lecture, and you won't see most of it for the rest of the class, except for in the following way. Chi-squared, done. Let's talk about the t-distribution. The t-distribution is super cool because it accounts for the fact that while the normal distribution, you'll remember, needs us to know the exact sigma squared and mu for this random variable, the t-distribution is going to account for the fact that we can't quite know this perfectly. We can only estimate it based on a sample, right? So that's why I said in the last video that this e of x and b of x and this mu sigma squared, they're going to be a little bit shifty on us later, and this is where it's going to come in, right? This t-distribution is also going to be a bell curve. That's the cool thing, okay? It's going to be centered at 0, which is super nice. And as it's, in fact, I got to give this to you really quick. Let's say, for example, we have a random variable t, big T, is distributed as a t distribution with, again, degrees of freedom nu. This is nothing new, if you will. This t-distribution of mu is going to have its expected value at 0 always. The t-distribution with its PDF and stuff like that, I could show it to you really quick, and I will once we pull the table up again. Its expected value is always 0. It was designed to be centered at 0. And its variance has a fun, funky little... formula, but its variance, the interesting thing is that its variance approaches 1 as your degrees of freedom approaches infinity, which means as your degrees of freedom gets bigger and bigger and bigger and bigger. And later what this is going to mean is as the size of your sample gets bigger and bigger and bigger and bigger, if your thing is distributed as a t-distribution, it will turn into the standard normal distribution because its expected value is always 0 and its variance will approach 1. So it's super cool. All right. We have the PDF. It's gross. And again, we have the CDF approximated in a table, right? Sorry, it's getting a little late. I'm a little tired, so this one's a little bit slower. But here's the deal, okay? This table is also different. But the one thing you need to understand about a t-distribution and why it's cool is the following thing, okay? Where did it go? I have it right here. Never mind. I'm not going to tell you about that. We'll talk about it later. But for now, let's just look at the table and talk about how to read the chart because it's a little late and I'm getting a little tired. So that's my bad. But I want to get this out so like the test opens tomorrow for the people who are already in the class. So I just want to make sure that this gets done. Maybe later we'll come back and revisit some of this, but also in later lectures we'll delve into this a little bit more. Let's just talk about how to read the t-table. So first, this z-table right here had a highlighted part to the left. The chi-squared table had a highlighted part to the right. And the t-table does not have either of those. Super obnoxious, right? Hopefully I don't have to point out to you at this point, but there can be many different t random distributions. You could have t of like 6. You could have, you know, t 2000. Something like that, right? Okay? So what this t-table does is it does something similar to what the chi-squared table does in that it takes the degrees of freedom and puts them down to the left. So every row is coming from the same distribution. But it does a different thing with its columns, okay? Let me just read you what this says, and we'll talk about this picture really quick, and I'll draw it so that I can like point out to you what I'm talking about as we're looking at it. Right? T star, negative T star, and C in the middle. Here's what I'm going to tell you about, okay? The table entry for P and C is the critical value T star with probability P lying to its right and probability C lying between negative T star and T star. What does that mean? Let's talk about it. If I'm on, let's just pick a row, the T degrees of freedom 1 distribution. That is a different distribution from the T degrees of freedom like 10 distribution, right? So let's say we're looking at the 10, right? We're in row 10, degrees of freedom 10. That is a specific curve. It looks a specific way, okay? It's a little bit steeper than the degrees of freedom 1 table, but it's a little bit wider at the tails than like the degrees of freedom 1000 T table, or T distribution, right? The graph. There are 3 different ways that you can read this table. Okay? You can read it by the top row, which is confidence level C. That's this piece here in the middle. Okay? If, for example, I wanted to find the value of the T6 distribution such that the probability that T is less than, I don't know, some number is equal to 0.05. Okay? There's 3 ways I can do this. Given that, let's just say, for example, that T, let's make these the same color so that they kind of connect in our mind, okay? If I know that T is distributed as a T random variable with 6 degrees of freedom, what is the value on the T table such that I expect big T, the random variable, to take on a value less than little t, the value, for only 5% of the time? Let's figure that out. 3 different ways, okay? And it all comes down to this picture right here. So the one thing I want to point out to you is I want to find a number that has to do with the left side of the table, right? I have a less than question. So I'm looking at the left side of some number. I want to the left of some number to be 5%, which means I need to find a negative T star. How am I going to find that? Well, if I have 5% to the left of some number, then that means, because the t distribution is symmetric around 0, that I have 5% to the right of the positive version of that number, okay? And what that also means is if I have 5% to the left of that number and 5% to the right of its positive version, then in between those two, I have to have 1 minus 5% minus 5%, right? All the rest of the area that's left is 90% of the area under the curve. So these are the three ways that we're going to talk about reading this table. On the top, confidence level C, 90%. Okay? In this case, I want this number right here, some negative t star. Okay? And I want it such that I have 5% of the distribution to the left of that number, which means I'm going to have 5% of the distribution to the right of its positive version, which means I'm going to have 90% in the middle. That C is going to be that 90%. We'll talk about why that's a confidence level later when we start talking about things like confidence intervals. It's going to be super cool. But for now, all we need to know is how to read the table. So let's go to the degrees of freedom 6 table, or the degrees of freedom 6 row, and then let's go to the 90% confidence level column, okay? Because confidence level C, we figured out by drawing this picture, is 90%. Again, drawing these pictures is going to be huge for you. Give yourself these little brackets. Organize your thinking. It's going to be super nice. Row 6, we're zooming around. Row 6, 90% column is going to give us that T star is equal to 1.943. And we say, aha, we're done. We found the number, right? This question mark has to be equal to 1.943. And then you laugh and you say, Tommy, you're wrong. And I say, why am I wrong? And you say, well, look, if you put 1.943 on the graph, you're putting it right here. That has 95% to the left of it. And I go, of course. How could I forget? I have to take the negative version of the number that I got from the table, okay? So it would be equal to negative, right? It would be negative T star because I'm looking for a less than thing. That's just how we read the table, okay? That's everything we really need to talk about the t distribution right now, because again, you'll have things like, how do I find the expected value? You don't actually have the t distribution on here. But basically, expected value is 0, and then the one thing you will actually have to remember, which is not on the chart, so let me give that to you. The variance of a variable that is distributed as a t random variable is equal to, let's see, I have it here, the degrees of freedom over the degrees of freedom minus 2. And the expected value of a t random variable is always 0. So the one thing you have to memorize that is not on the chart is this right here. So hopefully that will be helpful to you on the test. It might be. I can't remember. I know I helped write the test, but I can't remember if it's on there or not. Okay? Let's just point out really quick the difference between all of these tables, and then we'll cover briefly on why these tables are cool. Okay? Z table. Standard normal. In the middle are the probabilities. They are the areas under the curve to the left of the number that you get by going to the row for the first 2 digits and the column for the 3rd digit. Okay? Boom. These are the p-values, or the probabilities, or the areas under the curve. Those are all the same thing. Come back to the chi-squared. Now we have alpha representing a probability. It's to the right. But now the alphas, the probabilities, are only columns. And because we can have different graphs, we're not standardizing chi-squared in any way, like we are with the normal variables. We actually have to represent a different row for each different graph, each different distribution. Chi-squared 1, chi-squared 28, they have to have different numbers. And so these numbers in the middle of this table are not probabilities like they are up here. These are probabilities in the z table. Down here on the chi-squared table, these are the actual values. They're the values you would get from the left column in the top row of the z table, except, they're different because like these ones are, they get absolutely massive. And we'll talk about why later. It has to do with the fact that chi-squared is a variance thing. But basically, in the middle are the values. On the columns are the we've disappeared. On the columns are the probabilities. And on the left is what does your distribution look like? Which distribution are you looking at? Okay? And then over here we have different ones as well. And then not to stress too much, but again, this one has alpha on the right. Z has alpha on the left. And then this t table looks a lot like the chi-squared table in that in the middle here you have the actual values, the numbers on the graph, right? To the left, you have a degrees of freedom column that tells you what does the graph you're looking for look like. Is it T5? Is it T24? Is it T1000? Or is it so big that you might as well just use the numbers from the Z table, Z star, right? The one other thing I didn't show you about the T distribution that we're going to show you now, you remember this number that we got, negative 1.943. We got it from row degrees of freedom 6, and we got it from the confidence level 90% column. Well, if I take a look down the 90% column, okay, if I go all the way to the bottom, I'm in the 90% column. This is where I found my 1.943 in row 6. If I scroll all the way down to the bottom, I have these bottom two columns that are different. They're the one-sided and two-sided rows, not columns, my bad. Notice in this column, the 90% column, I'm going to make this big again so we can show it. The one-sided value is 0.05 and the two-sided value is 0.1. So we had confidence at 90 or 0.9 and we have one-sided as 0.05. What do you think that could refer to? Well, it's the area underneath the curve to one side of either T star or negative T star. One-tailed, one-sided is 5%. Two-sided or two-tailed, 10%. So if you're stuck on C and it's confusing you and you don't want to do it, don't. Just use the one side. Draw yourself this graph and say, hey, I wanted to find it such that the probability of T being smaller than a number was only 0.05, right? So I have to pick the number that has 0.05 or 5% to the left of it, right? And so I can go to the one-sided value. I can go back up to 6, 1.943, and then just make it negative because it's a less than thing. That's going to cover everything you really need to know about how to read these tables. We'll talk about more like what sense they make and what they actually mean later, in later mini lectures. For now, just knowing how to find these values is going to make learning what they actually mean a lot more helpful. And a lot, well, not helpful, but it's going to make it a lot easier to learn like the applications of the thing if you're not hung up on how to calculate the values and what the values are actually telling you. So that's why we spent so much time on that. Now we're just going to spend a brief moment, that's a Spanish word. Now that we've actually talked about the T distribution as well, let's talk about the central limit theorem and just make a couple of notes on it really quickly, okay? The true mean of a random variable is something that we can't know, right? For example, if I wanted to take average GDP of a state, right? Average state GDP in the US. We have 50 states in the US currently. So if I got all 50 data points and I put them in here and then I took their average, that would give me a number. And you might say, well, that's mu. That is what the average state GDP is in the United States, no matter what. And then I would say to you, well, what if we added Puerto Rico as a state, or Washington, D.C.? They both have populations bigger than Wyoming, and we own both of them. Why don't we add them as states, right? That would change this number. And now all of a sudden we're thinking, oh, okay, hold on. Average state GDP in the U.S. is probably a thing that we don't actually know. What we currently have is we have a 50-state sample of state GDPs in the United States. But we could hypothetically take a 42-state sample, or we could take a 2-state sample, or perhaps in the future we could take a 75-state sample. The thing is, we'll never know, because we can't add infinite states to the union. And so we have to move away from this mu, right? This mu, this true average state GDP in the United States, is a value that we don't know. But we can get really close to it. We can get really good at guessing it. And now what we're going to introduce to you is this X bar notation, or this, Y bar notation. And this is not going to mean complement like it did way back at the beginning of the class. This is going to mean sample average. X bar is just going to be equal to 1 over n times the sum of xi from I equals 1 to n. This is literally just add them up, divide by the number of things there are. We're well acquainted with this. This is also the formula for the expected value of x, okay? This is why in the last video I was telling you that E of x and V of x and mu and sigma squared are going to get fuzzy really quickly. We'll talk about it more in the next lecture, okay? But for now, what you need to know is the following thing, right? One thing I need to point out to you, I will do using the uniform distribution, okay? This is just what we're going to talk about. What is the probability of, or, what is the F of 2 dice rolls, right? What is the PDF for outcomes of rolling 2 dice? It's discrete, right? And it looks like this, okay? Well, first of all, let's talk about this, right? What is the PDF of 1 dice? Okay. If I just roll 1 dice once, what are the possible outcomes? Well, I can get 1/6 chance. I'm skipping steps here, right? But what that is, if x is 1, x is 2, x is 3, x is 4, x is 5, x is 6, right? These are even across. If I wanted to draw it, it would look like this, right? It would be bars, just like we did before. This would actually be 7, but it would be dotted because you can't actually hit a 7, but they need to be 1 block wide, right? So 1, 2, 3, 4, 5, 6. Okay, I've drawn too many of those. 1, 2, 3, 4, 5, 6, 7, right? And we'd have our little blocks here in our histogram. You have an equal chance of hitting each of these, and it's at 1/6, right? This is the 1 block, the 2 block, the 3 block, the 4 block, the 5 block, the 6 block. 1, 2, 3, 4, 5, 6. Yeah. So it's only going to extend to 6, right? That histogram. Okay. That's what it looks like. They all have an equal, even chance of showing up. Now, here's the question. What is F of 2 dice? Well, hopefully you'll notice the following thing. This is not going to be even probabilities anymore. Why? If I roll a 6 on the first dice, what can I hit? Now I could hit a 7, 8, 9, 10, 11, or 12. But what if I only hit a 5? Can I hit 12 anymore? The answer is no. I could hit a 6, 7, 8, 9, 10, 11. I no longer can hit 12. It's less likely that I hit 12 now, which is pretty interesting. And in fact, that graph is going to look like this, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Something like that, right? Where this is 12. Okay? The most common dice roll is a 7 because no matter what I roll on the first dice, I can get 7 from the other dice, right? If I roll a 1, I just need a 6. If I roll a 4, I just need a 3. If I roll a 3, I just need a 4, right? So 7 is the one that's going to show up most often. And things like 2, where I have to hit 2 1s, as opposed to hitting a 1 and a 6, or a 6 and a 1, or a 2 and a 5, if I have to only hit 2 1s, that one's going to show up the least. It's 2, so this isn't actually 0, but that's fine. We'll just block that out over here, just like that. It's a little ugly, but again, we're giving me some credit for drawing these graphs, right? You'll notice that this is curved now. What do you think would happen if we rolled 10 dice, or 20 dice, or 1,000 dice, or 1,000,000 dice? What do you think is going to happen here? What's the average dice roll going to look like? What's going to happen? Well, what's going to happen is we're going to get a distribution that starts to look like this, right? How does this make any sense? Okay. Let's say you were to take the average state GDP for just one state, okay? That distribution looks like this. It could probably be anything, okay? What if you take the average state GDP for 2 states? Then it's going to start to look like this, where if they're both really high GDPs, you'll get something way out here. And if they're both really low, you'll get something way out here. But if one of them is high and one of them is low, you'll end up here. Or if if they're both in the middle, you'll end up here. Or if one is moderately high and one is moderately low, you'll end up in the middle, right? So you start to see that as you add more and more observations, more and more pulls of the data, or trials, or dice rolls, if you will, dart throws, potentially, the more you're going to trend towards middles, the more you're going to trend towards averages. And that is the central limit theorem, that as n approaches infinity, our sample mean, right? So this is 7 because we just totaled it, but if we divided by the number of dice that we rolled, this would actually be the 1 block, right? And this would be the 6 block over here. We'd have 5.5 and so on, and we'd end up with an average of 3.5. As n approaches infinity, x bar is going to approach the true mean. Something to think about, right? How does that make any sense? Let's say, for example, that the true mean of averaging dice throws is 3.5. And that's something that we know because it looks like a uniform distribution. If I roll this as often as I roll that, 1 plus 6 is 7 divided by 2, that's 3.5, right? The true mean of a dice roll, the expected value of a dice roll, is 3.5. That is always true, okay? That comes from it looking flat. But what about a million dice roll? If I wanted the expected value of, not the sum of a million dice rolls, but just like the average of a million dice rolls. So let's just call that dice bar. That's also 3.5, right? This is like the true value, okay? This is what we know is true, just based on how dice are made. Are you ever actually going to roll a 3.5? No, you can't. But on average, you should expect to roll around 3.5. If you sampled a million dice and averaged them, 3.5 is going to be the biggest bar by like a million years, right? If I threw a million dice, the chance that I roll 6 million is literally 1 in just a colossal number of outcomes, right? I would have to roll a 6 on every single die for a million die. That's insane. Likewise, if I only wanted a total of 1 million or an average of 1 across 1 million dice rolls, I would have to roll a 1 on every single dice. But if I wanted an average roll of 3.5, there's so many ways to get that. It's easily the most likely. That graph is going to look something like this. It's going to be crazy. But if my sample is only 2 dice, right? If I only throw 2 dice, then my average from that sample could be like 1.5 if I rolled a 1 and a 5. No. If I rolled a 1 and a 4. No. If I rolled a 1 and a 2. That would add up to 3 and sample average would be 1.5. The point being is like when your observations are low, you get a lot of variation out here. That's one of the reasons that like the t-table or like the normal table from before, why these tails get taller as the variance gets bigger, right? They get taller because you see these extreme results more often. But as you increase the number of observations, you're going to converge on what we know is the actual average. X bar, your sample average, is going to approach the true average that we really can't see. And so once n gets big enough, we're confident in saying, X bar is a great estimator for the true mean because of the central limit theorem. And then we're going to use that and abuse that like nobody's business. The one other really nice thing to tell you about this is that X bar, a sample average, right, is in itself a random variable, right? You can get a bunch of different sample averages depending on which states you sample, how many states you sample, and how many times you run the sample, right? So X bar is actually distributed as a normal variable with the true mean mu and variance sigma squared over n. That's a pretty cool thing to learn. We are going to use that so much soon. For now, that's just a nice thing to know. And that's going to cover everything we need to know about the chi-squared and t distributions and everything we need to talk about the central limit theorem for now. Everything else, this is where we're heating it up. We're putting dinner in the oven. We've just turned the dial and closed the door. It's just about time to start eating, okay? Today in the lecture, chi-squared distribution, t distribution, the central limit theorem. That was great. We covered it. We covered everything you need to know. We reviewed where you can find that useful chart if you'd like. And next time on our mini lectures, we're going to talk about what I have just previewed for you, estimators, and what they do and what they are and their properties and the cool things about them. And the fact that we're going to use these estimators like telescopes to try to see planets that we could not otherwise see with our naked eye. Okay? We're going to try to use estimators to estimate population or true values. Okay? That's what we'll be doing next time. As always, if you have any questions, sorry this one didn't end up being, I think this one might have ended up being the longest one yet, but reading these tables is actually so important that it's worth your time. Thanks, of course, as always, for stopping by the lab hours. Apologies for being a little bit tired this time, but hopefully we get this out to you in a time period that is helpful and you find helpful information. As always, if you have questions, if you're in the class, email tmorg.ta@gmail.com. If you're not in the class, email labhours@tmorg.org, or just leave a comment. That's probably the easiest way. Like, subscribe, share, you know the drill. Thanks for stopping by. We'll see you next time. We'll talk about properties of estimators. It's been a pleasure, and have a wonderful day.